This video is brought to you by mywayteaching.com.
In this part, we are going to study about another one important concept, that is reflection of waves. See, so far we considered waves which are propagating in an unbounded medium. What happens if a pulse or a wave meets a boundary? If there is a bounded one end, if that wave or a pulse, if it meets that boundary, what exactly happens? If that boundary is rigid, the pulse or wave gets reflected, isn't it? Obvious. And the phenomenon of echo is an example of reflection by a rigid boundary. So, in a house or in acoustic buildings, we hear echoes, right? Why that? This is due to the reflection of the sound from the rigid walls, isn't it? So, if the boundary is not completely rigid, or if it is an interface between two different elastic media, the situation is somewhat complicated in that case, because in that case a part of the incident wave is reflected and the part is transmitted to the second medium. If the wave is incident obliquely on the boundary between two different media, the transmitted wave is called as the refracted wave. See, if the this is a boundary, if the wave, if it is moving like this, and this transmitted wave to the next media, this is one media and this is another one media, and this is the boundary between these two media. Okay, then the wave which is transferred to the next medium, it is called as a refracted wave. The incident and refracted waves obey Snell's law of refraction. We know that Snell's law, right? N1 sine theta 1 is equal to N2 sine theta 2, where N1 and N2 are the refractive indices of medium 1 and medium 2. This is the Snell's law. And the incident and reflected waves obey the usual laws of reflection. This is the incident wave, and if it gets reflected like this is the reflected wave. This is the incident wave. Isn't it? Yes. So this is about a little information about reflection of waves. You can see this figure. In this figure, a pulse incident from the right is reflected at the left end of the string, which is tied to a wall. Okay, here it is the wall which is tied here. A pulse which is no, it is incident from the right, it is reflected from the left after hitting this wall. The reflected pulse is inverted from the incident pulse. Okay, that is the figure A. In figure B, the left end is tied to a ring that can slide up and down without friction on the rod. Now the reflected pulse is not inverted by reflection. In this here, this left end is tied. The reflected wave is not inverted in this particular case. Here it is inverted, isn't it? So in this figure A, you can see that the pulse traveling along a stretched string, and it is being reflected from that boundary. Assuming that there is no absorption of energy by this boundary, or we can say this walls, The reflected wave has the same shape as that of the incident pulse, but it suffers a phase change of pi. Or isn't it? Here you can see this, it has no change in shape, but there is a phase difference of 180 degree once it is reflected from this boundary. By the principle of superposition, this is possible only if the reflected and incident waves differ by a phase angle of pi, so that the resultant displacement is zero. This reasoning is based on boundary condition on a rigid wall. See, as the pulse arrives at the wall, it exerts a force on the wall. By Newton's third law, the wall exerts an equal and opposite force on the string, isn't it? So if this is a rigid wall, as this pulse, it moves towards this wall, this pulse exerts a force on this wall. In return, this wall exerts an equal and opposite force on this pulse by Newton's third law of motion, generating a reflected pulse that differs by a phase of pi. If on the other hand, the boundary is not rigid, if you consider this boundary, what we are considering, if it is not rigid, completely free to move, but it is completely free to move, such as in the case of a string tied to a freely moving ring on a rod, in that case, the reflected pulse has the same phase and amplitude as the incident pulse. Here we saw in this second one, there is no, the reflected wave is not inverted, but in this case it is inverted, isn't it? So the net maximum displacement at the boundary is twice the amplitude of each pulse in that case. So in order to summarize these two cases, we can say a traveling wave at a rigid boundary or a closed end is reflected with a phase reversal, but the reflection at an open boundary takes place without any phase change. Mathematically, to express this, we can write y2 x comma t is equal to incident traveling wave is y2, that is equal to a sine kx minus w t. This is the incident traveling wave. At a rigid boundary, the reflected wave is given by, if the boundary is rigid, then the wave is reflected. So that reflected wave is given by, we'll represent it using yr, which is equal to, so there is a phase difference of pi as we studied now, isn't it? So this wave is inverted. At an open boundary, the reflected wave is given by, open boundary means if the wall is not completely rigid, the another case that we studied now, the reflected wave is not inverted in that particular case. So that reflected wave is same as that of incident wave, because there is no phase difference between the incident wave and the reflected wave in the open boundary case. Isn't it? So at the rigid boundary, y is equal to y2 plus yr is equal to 0 at all the times. Now let us study about standing waves and normal waves. What are these standing waves and what are these normal modes? See, now just we studied about the reflection at one end of the boundary, but there are some familiar situations. A string fixed at either end or an air column in a pipe with either end closed. You can assume that an air column with pipe with both ends closed, in which reflection takes place at two or more boundaries because both ends are closed there. In a string, for example, a wave going to the right will get reflected at one end, which in turn will travel and get reflected from the other end. So this will go on until there is a steady wave pattern set up on a string. So such wave patterns are called as standing waves or stationary waves. Okay. If both the ends are fixed and continuously the wave it gets reflected from both the ends, isn't it? Still there are, okay, this goes on until there is a particular wave pattern, and those kind of wave patterns are called as standing waves or stationary waves. So to see this mathematically, you just consider a wave traveling along the positive direction of x-axis and a reflected wave of the same amplitude and wavelength in the negative direction of x-axis. Okay. In that case, with pi is equal to 0, we get that we just now studied a sine kx minus wt a sine kx plus wt. The resultant wave on the string, according to the principle of superposition, so if you add these two, we get the resultant wave. So using the trigonometric identity that we already know, that is sine a plus b plus sine a minus b is equal to 2 sine a cos b We know this identity. So using this, applying this identity to the above equation, we get y of xt is equal to 2a sine kx cos omega t. See, from this wave equation and the one we studied before, that is y of x comma t is equal to there is a difference between these two equations. This equation that we studied before, compare these two equations, the terms kx and wt appear separately. The amplitude of this wave is 2a sine kx, isn't it? Thus, in this wave pattern, the amplitude varies from point to point. But each element of the string oscillates with the same angular frequency w. And there is no phase difference between oscillations of different elements of the wave. The string, if you consider, it vibrates in phase with differing amplitudes because that amplitude varies at each point. At different points, the amplitude will be different. So the wave pattern is neither moving to the right nor to the left. Hence, they are called as standing or stationary waves. The amplitude is fixed at a given location, but it is different at different locations. The point at which this amplitude is zero are called as nodes. The points at which the amplitude is largest, we call them as antinodes. Where amplitude is zero, we call them as nodes. Where amplitude is maximum, we call them as antinodes. Okay.